Good day to all of you. So today I'm going to talk to you all about two-factor analysis of variance. So this is two-way ANOVAs. Now, in the previous videos, we already have discussed about one-way ANOVAs and also how to manually compute one-way ANOVAs. In addition to that, I also have discussed about two-way ANOVAs. But now, today, the reason for this discussion is to show, or rather demonstrate, how the two-way ANOVA functions, and also more than that, I'm also interested in demonstrating to you how the manual computations would work. But before going through this video, I would encourage all of you to go through one-way ANOVA video and also two-way ANOVA video, and also there's a mixed factorial design video as well. Now, all those three videos were completed using the software Jamovi, and then once you go through it, the lessons would be much more clear to you. And then upon understanding that, following through this manual computation would make more sense. So, without further ado, let's get with the lesson. Get on with the lesson. So two-way ANOVA, so two-factor analysis of variance. So once again, this is independent measures. Now, what are we going to discuss? First, we are going to have some discussion about the basics of two-factor ANOVA or a two-way ANOVA, and then we'll be having an in-depth discussion about main effects and interactions, how to identify main effects and interactions, and what kind of preliminary things need to be ensured if we are to go ahead and assess something like that, and also about what kind of hypotheses are required in this kind of an endeavor. And then in addition to that, I will also briefly touch upon notation and formula that is required for our manual computations. And in addition to that, finally, we'll also discuss about the results interpretation from the two-factor ANOVA. And also I have included a little bit about effect size calculation, how to calculate eta squared and partial eta squared from a two-way ANOVA output. Now, let's try to understand why exactly a two-factor ANOVA is required. Now we know if we are to find significant differences between two groups, a t-test is ideal. And if we are to find differences between two or more groups, uh, of course, for two groups, we can go for a t-test, but if it is more than two groups, we can go for a one-factor ANOVA or a one-way ANOVA or the conventional ANOVA. The reason why I call this a one-factor ANOVA is the three groups are always, uh, it derives from the same factor or the same independent variable. For example, the type of drug and its effectiveness in alleviating anxiety, for an example. So anxiety can be alleviated by certain drugs. So drugs is the independent variable, and there could be two drugs. So if you have two drugs and you want to find mean differences, that's going to be a t-test. If you have more than two groups and you want to find mean differences, that's going to be a one-way ANOVA. Why do I call it a one-way ANOVA? Because I have only one independent variable, and that independent variable in this example I just said is the type of drug. So a two-way ANOVA or a two-factor ANOVA is required in instances when you have more than one independent variable, which means you have another factor, and this second factor would also have its own groups. So in such a situation, you should, of course, go ahead and use two-way ANOVA. Now, let me give you an example here. Here you would notice a table, and on the left side, you have factor A, that is humidity. And on the columns, you would see factor B, that's the temperature. Now, one could say, here I haven't specified what exactly is meant by performance. Let's say performance on an exam or something like that. One could tell humidity has something to do with performance. Another person could say temperature could have something to do with performance. So if you have your study where you have specified humidity has something to do with performance, here you have two groups, low humidity and high humidity. If you want to just measure the performance between low and high humidity, in that case, you will only need to run independent samples t-test because you just have two groups. and both the groups belong to factor A, which is humidity. And then here you have temperature, which is factor B. Now temperature, there are three specific conditions: 70 degrees, 80 degrees, and 90 degrees. So this is in Fahrenheit. So here you have three groups. So if you are to find differences for performance just for these three groups, then that would be a one-way ANOVA once again. But if you notice here, we just don't have three separate groups and two separate groups. We actually have a combination of both of these. So this is what we call a 2 by 3 design. Why do I call it a 2 by 3 design? Because I have two groups of humidity and three groups of temperature. Altogether, I have six groups. Those who have low humidity and in the 70 degrees room, what is their performance? What's the performance of low humidity and 80 degrees? What is the performance of low humidity and 90 degrees? And the same goes for high humidity and 70, high humidity and 80, and high humidity and 90. So I have given three questions here. I got this from Gravitaire book. So if you go through this, it has what happens to the mean level of performance as the temperature is changed from 70 to 80 and 80 to 90. Now that focus in that particular question, the focus is on one independent variable and one dependent variable. So it is not factorial. How about the second one? What happens to the mean level of performance as the humidity is changed from low to high? Once again, we are investigating another factor and its impact on the dependent variable. But if you go through the third one, here's how it get combined. How do specific combinations of temperature and humidity affect performance? For example, increasing humidity may have no effect on performance when the temperature is low, but it could be disruptive when the temperature is high. So you see how this differs. So we are interested here in the combination or the combined effect of both these independent variables. Now for this, we need to run factorial ANOVA or a two-way ANOVA, or in other words, a two-factor ANOVA. In this, we have to have three hypotheses, and for the three hypotheses, we need to have three separate F ratio tests. Now, first, let's understand what exactly this F ratio test is going to be. So the three F ratios of a two-factor ANOVA has the same basic structure. F equals to variances between the treatments divided by variances expected if there's no treatment effect. Now, at this point, this might not make too much of sense, but that is okay because we need to further go ahead and understand different elements because this is the final bit. So this F ratio is the final bit in our entire computation. But before this, we need to go through a series of other calculations as well. So it would be great if we can go through that first so that we would be much more confident when we go through F ratio. So I have already uploaded another manual computation video earlier. It has some of the most basic calculations as well, like how to get sum of squares and all of that. So here in this video, I haven't displayed how to calculate sum of squares and all. But if you go through the previous video, I have given the link down below. So if you go through that, you can pretty much understand more about how to do the basic descriptive calculations that are required for you to go through this one-way ANOVA, the two-factor ANOVA. Okay, now let's once again focus on the main effects and the interactions. So identifying these things are very important before you develop your hypothesis. Now, I told you for a two-factor ANOVA, there are three hypotheses. Two of the hypotheses will be for checking the main effects of the two factors. And the third one is to actually go ahead and check the interaction effect of the two factors. Now let's try to understand this. Here we have factor A, humidity. Now humidity scores are given for 70-degree room, 80-degree room, and 90-degree room, both for low humidity and high humidity. So performance scores are given for these particular variations. So variations in room temperature and humidity. Now, on an average, low humidity group has a performance score of 80. high humidity group has a performance of 70. So you can see performance has dropped 10 points from low to high humidity. So this is a noticeable difference between humidity and performance. So noticeable difference in performance based on humidity, which is something you can notice if you get the average scores for the two rows here. Now, in this example, factor A is given in the rows. That is why I refer to the rows. But if the factor A and factor B are swapped in positions, then of course we will be looking at factor B for the rows. But in this example, factor A is in the rows, so I'm interested in understanding the differences, the average performance score for the two conditions. So observing this is the main effect of factor A. This is factor A's main effect. So if this difference is significant, statistically significant, then we can observe main effect of factor A. And we can similarly observe the key differences between the three conditions, which are, our three columns here, which is factor B. Factor B is the temperature. When the temperature varies from 70 to 80, 80 to 90, on an average, we can see the performance has dropped from 80 to 75 and 75 to 70. So we are interested in seeing how this significance occurs as well, or with how whether this variation is going to be statistically significant as well. And that is going to be the main effect of factor B. Now, factor A has a main effect, which is calculated, based on the scores we get here. And then we have main effect of factor B here. Very similar to this, we have interactions as well. Now, before we go through that, let's just, quickly go through this here. So the mean differences among the levels of one factor are referred to as the main effects of that particular factor. That is exactly what I just demonstrated you guys. See, this is main effect of factor A and this is main effect of factor B. Now, to evaluate this, you need to first come up with the two hypotheses. We need to come up with the hypothesis for our factor A, and we need to come up with the hypothesis for our factor B. Now, null hypothesis here I have given mu A1 equals to mu A2, but we are expecting there's going to be a difference between humidity conditions. So mu A1 not equal to mu A2. Very similar to this, our F ratio, the formula is going to be the same like we discussed earlier for factor A, and the F ratio is going to be, the formula is going to be the same for factor B as well. But if you notice in the hypothesis, unlike two groups in the first hypothesis for factor A, here we have actually three groups, because here we have three temperature conditions. If you recall from our example, here we have three temperature conditions. So in our hypothesis, we have mentioned mu B1 is not equal to mu B2 and is not equal to mu B3. Now we have the two hypotheses to check our main effects. So let's go through our interactions. So what exactly is meant by an interaction and how are we going to find an interaction? See, as it says here, an interaction between two factors occur whenever the mean differences between the individual treatment conditions or cells are different from what would be predicted from the overall main effect of the factors. So what this says is, if you notice here, the mean difference here we have on an average 80. Here we have on an average 70. These are differences or the variation between low humidity and high humidity. From low to high, the amount of points that are being dropped in the performance is 10. In the 70 degrees room, you don't see any such difference. This 10-point difference is observed in the 80 degrees room. But in the 90 degrees room, you see a sharp 20-point difference, 80 to 60. There's a drop, a noticeable drop. So what it means is, when the temperature is 90, there's a 20-point difference between low versus high humidity conditions. So this 20-point difference cannot be explained by this 10-point difference, which is accounted by the main effect for humidity. because here in the main effect that we observed, it's just 10 points. But compared to this, there's a 20-point difference here. This 20-point difference may have caused because of something else. So in this example, that something else would definitely be temperature. So then there needs to be some interaction between these two. So that is exactly what we are going to find. Once again, here the F ratio is going to be the same like in the previous examples. Now, the two-factor ANOVA consists of three hypothesis tests. And the first one is to find the main effect of A. We call it the A effect. And the second one is the B effect. We once again, that's the main effect of B. And then A-B interaction or A into B interaction. So this is the main piece that we are interested in finding. Now, a lot of students usually ask whether this A and B interaction is required in a factorial ANOVA or a two-factor ANOVA. Of course, and that's the exact reason why we have decided to go with the two-factor ANOVA. If you go for a two-factor ANOVA, you should definitely find whether there's an interaction. If there's no interaction, one could always ask why exactly you considered going for an interaction or to find an interaction through a two-factor ANOVA. So here in this example, there are three separate tests that you need to run to find the A effect, B effect, and also the A and B effect. Even though in SPSS and JAMOVI you get the output together, these are independent tests. They are independent from one another. The outcome for any one of these three tests is totally unrelated to the outcome of either of the other two. So because of that, you could see that some of these are going to be significant and some of these are not going to be significant. So like I discussed with you earlier, we are interested in the A effect, B effect, and also A and B effect. Here's the F ratio, variances between treatments divided by variances expected if there is no treatment effect. Now, we need a little bit of formulas and notations here as well. Now, to generate the variance that is required to do our ANOVA calculations in usual ANOVA computations, the variance is known as mean square or MS. For this, you would require sum of squares and degrees of freedom. Now, sum of squares and degrees of freedom has to be calculated. If you watch my previous video on manual computations, I have explained it very clearly how to get the mean and also sum of squares. Now here we have some hypothetical data, but this is for a different study. Here we have arousal level and difficulty. So for example, here arousal level, we have three groups: low, medium, high. Difficulty, we have easy and difficult. Now, if you go through the scores here, low arousal, easy conditions, you have a mean of 3. Arousal, medium, and easier condition, you have a mean of 6. And likewise, you can see the main kind of fluctuates. And then here you have T. T actually stands for the treatment conditions total. If you add this all up, this will be 15. So 3 plus 1 is 4, plus 1 is 5, 6 is 11, plus 4, that's 15. That's the T here. Similarly, this one, medium group, for easy it has a T of 30, and for the high group it has a T of 45. And these are the sum of square values 18, 28, and 26. Here the T rho 90, that is the combination of all these three T's, 15, 30, and 45. So we call it the T rho 1, that is 90. So when you want to find the main effect of factor A here, these T rho values are very important. The same is done for the difficult condition as well. T rho 2 here is once again 30. And we have done the same for columns as well. The T columns here, that is 20. 15 here, 5 here, that is 20. This one is 50. This one is also 50. Okay, and it has separate sum of squares as well. So sum of squares are actually derived from here, these ones. This 8 is from this, 20 is from this, and so on. And then you have n is the total number of individuals who have participated in this study, that is the 30. G actually stands for the sum of all scores in the research study. This is the grand total. Grand total means combination of all of this. Here you have 90, here you have 30, so 90 plus 30 is that's 120. And then you have sigma x squared. Sigma x is the sum of scores we know, and then the square root of that one is 840. So what it means is you have to keep on squaring these guys up, and then you sum it all, and then you would be getting sigma x squared, that is a 840. Now, here's the terminology I have given. K is the number of treatment conditions. Simple N stands for number of scores in the treatment. Capital N, total number of scores in the study. Sigma X, sum of the scores. T is the treatment condition. And G is the grand total. Now, the calculations are going to be of two stages. Now, let's first go through the stage 1 of two-factor analysis. Here, in this one, we do this to first separate the total variability into two components, the between treatment one and the within treatment one. So first, let's find the total variability. Total variability, or the SS total, that is calculated by sigma x squared minus g squared divided by n. Now here sigma x squared is 840. Now how do I get this value? Sigma x squared is here, that is 840. That is subtracted by g squared. G here is 120. So 120 divided by 30, that is the n here. So here 30 is the n. So 840 minus 120 squared divided by 30, or over 30. So the answer is 840 minus 480, that is a 360. 360 is the total variability, and for this we are going to calculate degrees of freedom. We call this the degrees of freedom total. This would be n minus 1. N minus 1 would be 30 minus 1, then the answer is going to be 29. And then similar to this, we are going to calculate between treatments variability as well. That is t squared, sigma t squared over n minus g squared over n. Now, here's how we are going to do this. Now, we already went through the data in the previous slide. So, there are 6 treatment values, and each has 5 scores, and the between treatment sum of squares therefore is this t squared over n has to be done for all the 6 treatment conditions. For example, let's get the t value and the n value from our first group. See, this is the first group that I have. Here the t is going to be 15, and then the n is going to be 5. So 15 squared divided by 5. The next one is t is 30. 30 squared divided by 5. Likewise, you have to come up with the t squared and divided by 5, because all the groups have 5 in each. So here we have all these values, all the 6 groups. This is divided by g squared over n. It is the same thing that we have here, 120 squared over 30. And when you do this particular computation, the result is going to be a 240. So this is the between treatment variability. Total variability is 360. Between treatment variability is 240. I will just underline this so that you can easily notice what we just discussed. And we can generate a degrees of freedom for this as well. Here the degrees of freedom for between treatment is going to be number of treatment values, so t values minus 1. So we have 6 t values. 6 minus 1 is df between treatments. The answer is going to be 5. This one. right here. And then we can find the within treatment variability as well. To compute the variance within treatments, we first compute sum of squares and degrees freedom equals n minus 1 for each of the individual treatment conditions. Then the within treatment SS is defined as sigma SS each treatment. So SS within treatments is the sigma of SS each treatment. Now let's go through the SS here. See, these are the SSS, sum of squares 18, 28, 26, 8, 20, and 20 here. So that value is, it adds up to 120. The degrees of freedom for within treatments is, for each you have 5. So 5 minus 1 is 4. So you have 6 conditions. So 6 times 4 altogether is going to be 24. So this completes the first stage of our analysis. Now here, the two components always adds to the total variability. For example, if you consider within treatment variation is, what do you call variability is 120, this 120, and between treatment variability 240 adds up to a 360. The same goes for degrees of freedom as well. This 24 and here the 6 would add up to, the 5 will add up to a 29. 29 is the total, DF total, that is 29. Here you have for the between treatments 5. So 24 here and 5 over there would always come to a 29. So both the DF and SS values of between and within would always come to a would be equivalent to the score that you have for the total variability and total DF. Now with this, let's go for the stage 2 of the two-factor analysis. Now, this second stage of the analysis will determine the numerators for the 3F ratios. Now, once again, here we will determine the between treatment variance of factor A, factor B, and the interaction. So, factor A, to compute the sum of squares of factor A, we calculate between treatments sum of squares using row totals. Exactly the same we computed sum of squares between treatments using the treatment total t values earlier. Now, if you go through this, here we have two row totals, 90 and 30. See, 90, this is one row total, 90, and here we have 30 because we are going to find the main effect in what do you call the factor A. So for that, this is how we are going to do. This is your formula. Sum of squares for factor A, that is t square, sigma t squared rho divided by n rho minus g squared divided by n. Now we have t row scores, that is 90 and 30. 90 and 30. 90 squared divided by 15 because in each condition you have 15 participants, right? 5 here, 5 here, 5 here, so 15. Here also 15. Divided by g squared divided by n, that is 120 squared divided by 30. So 540 plus 60, that is 600. 600 minus 480, the answer is going to be 120. And degrees of freedom for this one is number of rows minus 1. So we have only 2 rows here. So 2 minus 1 is going to be 1. And then we are going to do the same for factor B. But here t column scores, you have 3 column scores, 20, 50, and 50. So 20 squared divided by 10, 50 squared divided by 10, plus 50 squared divided by 10 minus 120 squared divided by 30. The final answer is going to be a 60. And here the degrees of freedom is number of columns minus 1. Now we have 3 columns, 3 minus 1 is 2. And for the interaction, we have sum of squares A times or A into B. So here the calculation is sum of squares between treatments minus sum of squares A minus sum of squares B. So that one is going to be SS between treatments. We have done it earlier. That is 240. We have 240 here. And then we have to find sum of squares for A and sum of squares for B. Sum of squares for A is 120. Sum of squares for B is 60. So 240 minus, that's the SS between treatments. Sum of squares A, that is 120. So 240 minus 120 minus 60, the answer is going to be 60. And the degrees of freedom here is degrees of freedom between treatments minus DFA minus DFB, that is 5 minus 1 minus 2. Because this has come from treatment conditions, this one has come from the number of rows, and this one has come from the number of columns. So the final answer is 2. Now we need to go ahead and calculate our mean squares and F ratios for the two-factor analysis. So the two-factor ANOVA consists of 3 separate hypotheses. Like I mentioned, the denominator for each F ratio is intended to measure the variance that would be expected if there's no treatment effect. So here's our calculation, or the formula for our calculation. The within treatment variance is called the mean square, or MS, and it is computed as follows. Sum of squares within treatment divided by degrees of freedom within treatments. So sum of squares within treatment we earlier found, that is 120. This one. And then DF within treatments we have found along with that, that's a 24. So the final answer is 5. So the above is the denominator for all 5 ratios. So this is how we find the denominator for all F ratios. Now we already know what our F ratio is. In F ratios, the denominator is variances or the differences that would be expected if there's no treatment effects. So in this example that we discussed, the denominator is going to be 5 always. Now based on this, we can go ahead and do our calculations. Now here I have given on the right side the F ratio calculations. Like I mentioned, all the denominators are 5, you can see here. But before that, let's calculate mean squares. The numerator of the 3 F ratios all measure variance differences between treatments, differences between level of factor A, factor B, and also the interaction. Now, for this, first you have to calculate mean squares A, mean squares B, and mean squares A into B. Mean squares A is calculated by sum of squares A divided by degrees of freedom A, like this. So sum of squares A is 120, degrees of freedom A is 1, that would be 120. Mean squares B, sum of squares B divided by degrees of freedom B, that is going to be 60 divided by 2, that is going to be a 30. For the interaction, sum of squares A into B divided by degrees of freedom A into B, that is 60 divided by 2, that is a 30. For each one of this, now we have calculated F ratios. F ratios is for factor A, main effect, mean squares A divided by mean squares within treatment. So MSA here is 120 divided by 5. The F value is 24. And then for the next one, it is going to be 6. For the interaction, that is also going to be 6. Now these are larger F values. So what we need to do is you have to get this F value, and then you have to get the F distribution. Based on the degrees of freedom values, you need to go ahead and check whether it goes beyond the critical value. Now, factor A has degrees of freedom 1, and then denominator degrees of freedom is 24. So now, critical value of 4.26 for alpha 0.5 and a critical value of 7.82 for alpha 0.01. These are the critical values. Now our F score here is 24, but based on our degrees of freedom, the degrees of freedom values for a 95% confidence interval, that is alpha 0.05, the cutoff point is 4.26. This is from the distribution. Now, for the 99% confidence interval, that is alpha 0.01, here the critical value is 7.82. Now, we have obtained a F value of 24.00, which exceeds both of these. So we can claim that there's a main effect for factor A, and that also is significant at 99% confidence level. And we can test factor B as well. Here you have numerator degrees of freedom is 2, denominator is 24. Here you get for alpha 0.05 a cutoff point of 3.40, and for alpha 0.01 you get a cutoff point of 5.61. Again, here the obtained value is 6, which means it also exceeds both of these. So pretty significant. And the same goes for interaction as well, the same value. So that is also once again very significant because it has the same numerator and denominator DEFs, and as a result, it has the same cutoff points. Now here we can see all the required values, mean squares, degrees of freedom, sum of squares for all factors and the interactions, and also these are the final F scores. And now we can go ahead and interpret this. But before we go ahead and interpret, let's do a effect size calculation as well. Now the general technique for calculating the effect size for ANOVA is eta squared. This is the percentage of variance that is explained by the treatment effects, kind of like coefficient of determination is in correlations. So for a two-factor ANOVA, we compute three separate eta squareds. One measuring how much the variance is explained by the main effect of factor A. The second is how much of variance is explained by factor B. And the third one is how much explained by the interaction. So before we compute the eta squared factor A, we remove the variability that is explained by factor B and also by the interaction. So what I mean by this is something like this. Okay, give me a second. I think here I have mistakenly put, okay, like this. So here eta squared is calculated for the main effect A, that is sum of squares A divided by sum of squares total minus the sum of squares for B and A into B, the interaction, because we need to separate the amount of variance accounted by the factor A, and for that we had to remove the B and also the interaction. So because of this, since it is not based on the total variability of the scores, we often call this partial eta squared. Now, eta squared you can calculate for the total, model, like how much the entire thing actually explains. But here for factor A, we remove the variability explained by the B and also the interaction. As a result, the resulting the answer we are going to refer to it as it as partial eta squared instead of eta squared. So that's the difference between eta squared and partial eta squared. So as per this calculation, factor A explains 50%, factor B explains 33%, and the interaction also explains 33%. So you can see factor A is a significant the factor is, it has a significant effect, and also there's a noticeable, like a strong effect size as well. And this is the APA, what do you call, interpretation. The two-factor ANOVA showed a significant main effect for task difficulty if degrees of freedom, numerator and denominator, if value 24. This is the p-value. Why do we give this? Because 24 exceeds the cutoff point for alpha 0.01 as well. And eta squared, actually this has to be partial partial eta squared 0.50, or rather 50%, you can write it as 0.50. A significant main effect for level of arousal, and a significant of main effect for level of arousal as well. Here this one is also, once again, this is also partial eta squared, so I'm going to just write partial. That's the important aspect. And then a significant interaction between difficulty and arousal as well. For that also I'm going to write partial eta squared. These are all partial eta squares. Okay, like this. So this is the interpretation. Now, if you notice, I kind of went a little bit faster here. That's why I ask you to first review the previous videos on the playlist for the introductory ANOVA video and factorial designs, and then manual computations video for one-way ANOVAs and t-tests. And then you have 3 more videos on one-way ANOVAs and factorial ANOVAs and mixed factorial designs. So once you watch all of them, you would have a better understanding. And with that understanding, you can watch this video so that you can understand what exactly happens. So I included this video as to uh, not for you to do manual calculations by looking at this, but just for you to understand what exactly the process is going to be. So this video is not intended for you to learn manual calculations just by looking at this. This would be rather something that is good for students to understand the nature of the analysis or the manual computation. Since most of the students now only use software, this would be an added uh, lesson so that you would know how exactly manual computations occur. And some of this terminology also would become more familiar to you since you now know how exactly these manual computations occur. So this is exactly what I wanted to discuss with all of you today. And I will see you with a similar lesson in the future. You can access this lesson in Graviter and Volno 8th edition Essentials of Statistics for Behavioral Science. It's one of my go-to books for teaching research methods and statistics for our psychology students. So you can go through this lesson by yourself and also go through the examples further to understand how it works. So thank you very much for being part of today's lesson, and I will see you again with a similar lesson in the future.